Welcome everyone to the Network Heating and Cooling webinar. The title of today's session is the Circular Economy and Climate Responsive Buildings. I am Andy Smallbone. I'm an associate professor at Durham, and I'm also the Network Plus lead. This is our last seminar of 2022, and the event has been organized through the EPSRC Network Plus for the decarbonisation of heating and cooling, and is part of a series looking at the different challenges of decarbonising our heating and cooling sectors and behaviours. This month, we are delighted to welcome two speakers from Oxford University who will present their research in low carbon, climate responsive buildings and global production networks for cooling systems. But first, we'll hear from Jesus, who's a Marie Curie Fellow in the Energy and Power Group at the Engineering and Science Department at Oxford. He earned his PhD in low carbon buildings at the University of Seville in Spain, and after completing a BSc in architecture and MSc in building engineering. And he's been very busy doing lots of different postdoctoral activities, including his Marie Curie Fellowship projects in Spain, Morocco, and Saudi Arabia.
Thank you very much, Andrew. Thanks. First, I would like to thank for the invitation to present my work here in the Heating and Cooling Network. In this presentation, I will talk about low carbon, climate responsive buildings, looking at how to mitigate the impact of heat in the built environment. This is a work inside the framework of the Future Cooling Program of the Oxford Martin School, an interdisciplinary team working together to shape the future of cooling. And first, I would like to talk about where I come from. I am from Seville in southern Spain, a lovely place where you can find amazing food, fantastic weather, but this summer with some days reaching temperatures higher than 45 degrees Celsius, something that we never saw before. And this is because the way that we understand cooling is changing globally. Even though the highest request for cooling is located in the tropics, climate change is increasing the cooling demand globally. Cooling demand is expected to be more than triple by 2050, with heat events occurring more often and longer. So here we have the following question. What can we do to mitigate the impact of heat in the built environment? And to address this question in the Future Cooling Program, we are working together at different levels in order to mitigate climate change, the global warming, to reduce urban overheating, mitigate building overheating, and to address people discomfort more efficiently, decreasing energy needs. In this presentation, I will focus on how to address sustainable cooling in these three last scales. We need to consider that the adaptation of the built environment to warmer temperatures requires the deployment of the best available cooling techniques and technologies. Right now, a wide portfolio of solutions is already available to address cooling efficiently. These cooling solutions can be classified using 5 key concepts: solar protection, heat prevention, heat modulation, heat dissipation, and heat removal. The first one on solar protection is targeting the reduction of solar gains into the building envelope and openings. Heat prevention is based on the reduction of internal heat gains, mainly from lighting or appliances, insulation, and the improvement of air tightness of the building. With heat modulation, we target to increase the thermal energy storage capacity of the building to modulate heat. And with heat dissipation, we target to use an environmental heat sink at a lower temperature in order to dissipate heat using a low energy technique. In this case, we can use ventilation, evaporative cooling, radiative cooling, ground cooling, or water cooling. And finally, all the active technologies that we can find for heat removal. Despite this extensive portfolio, the main problem is that the easiest and the fastest response to address cooling still lies with the installation of an air conditioning unit, commonly regarded as the sole technological solution. This nominal market technology, the vapor compression refrigerant system, has become a long-standing incumbent in the cooling industry, creating barriers to innovation and transition, since cooling solutions are largely understood to take this particular form worldwide. These barriers can be grouped into 5 priority areas. This consists of, in the first step, building energy policies exclusively based on energy efficiency. In a second step, air conditioning only by temperature control rather than using other comfort parameters. The third one, building-centric design instead of occupant-centric design. The fourth one, in which we focus on product-based business models instead of a product-service model. And finally, we take all the attention on the standard operational phase of cooling. These 5 groups of barriers are fully explained and detailed in our last research article recently published in the journal Buildings and Cities. Now it's improved. Hopefully next week it will be available online. And I say this because in this presentation, I don't want to talk about problems and I want to give solutions. In the next slides, I am going to summarize the right steps in the right order that we need to do to address sustainable cooling, and how we can use these right steps in the right order to overcome these main barriers, where the vapor compression air conditioner should be part of the solution and not the sole solution. So the right steps to address sustainable cooling are 8, and implemented following the right order, they can increase the heat resiliency capacity of the building, they can downsize cooling systems and cooling needs, and finally mitigate resource consumption and the environmental impact associated with cooling. This step, of course, should be implemented considering current and future weather conditions, and of course, considering heating and cooling as a whole in the building design process. The first 4 steps are related to solar protection, heat dissipation, heat modulation, and heat prevention, and following this right order. These solutions are well known, but to be efficiently implemented, we need to overcome the first barriers group. First, building policies should move beyond energy efficiency metrics, and to start considering indicators based on the passive performance of building or passive survivability. I mean, considering buildings without air conditioning. For example, using indicators such as discomfort hours. Why? This that we did this year, published in Applied Energy, where we analyzed the mitigation potential of different passive cooling solutions from 2 different points of view. On the one hand, to reduce discomfort hours in those buildings, in buildings where we don't have air conditioning system in the y-axis, and on the other hand, in buildings where we have air conditioning in the x-axis. So in this case, we are targeting reduction of energy consumption, energy savings, and in this case, we are targeting reduction of the building of overheating. So in the upper area of the figure, we can find those solutions that can create synergies in those buildings where we have air conditioning and in those buildings where we don't have air conditioning. And here we find that the top solutions with the higher synergies are related to heat dissipation by ventilation or solar protection in roofs and windows. However, we have important trade-offs in cases of solutions to increase insulation or those solutions to improve the air tightness of the building. These solutions can reduce energy demand efficiently in cases where we have air conditioning. However, these solutions, in those cases where we don't have air conditioning, if we measure from the point of view of these passive indicators, they are going to increase the overheating of the building even more if ventilation is not properly addressed. Also, we need to consider the real weather conditions that the built environment is facing. This is one example of the city of Seville in Spain, where I come from. Here we find the problem of the urban heat island or urban overheating. This concept is associated with the urban areas that are significantly warmer than the surrounding rural areas. And this is important because there is a big difference in weather data from the official weather stations, most of the time located in rural or suburban areas, with the real urban climates. Most of the time, we are using exclusively weather data from these official weather stations to support the building design process. And in this example of the city of Seville, we see as we can find a temperature difference in some urban areas up to 7 degrees Celsius. Most of the time, these higher differences are located at night, as we can see here, where the magnitude of the urban heat island is much higher. This is important because it is not a problem only affecting outdoor urban environments, but also buildings and indoor spaces. And here I give one example. In this figure, we show the indoor temperature oscillation of the building in comparison with the outdoor temperature. In this case, in a well-designed building. So this will be the outdoor temperature oscillation and the indoor space. So first, if the building is not properly designed, addressing these 4 steps currently, overheating will increase by more than 5%. But additionally, if the building is located in one of these urban areas affected by the urban heat island, the indoor overheating will be even higher. As we can see, the building at night, where we have the highest magnitude of the urban heat island, we are decreasing the heat dissipation potential of the building, increasing overheating even more. But how much higher it can be? In this previous study, we calculated and demonstrated how this urban overheating can increase energy demand by close to 20% in those buildings where we have access to air conditioning. But at the same time, if we use passive indicators, evaluating the heat resiliency of the passive survivability of buildings, we see this urban overheating can increase discomfort hours by more than 30% in those buildings, for example, where we can find fuel poverty. So we need to start addressing these 4 steps properly, overcoming existing compliance tools to address building design, for example, SAP in the UK or Hulk in Spain. And if we address these steps efficiently, we have a great chance of eliminating the need of air conditioning. Even if not, we have different alternatives that we can implement to reduce even more the cooling needs and downsize cooling system. These are related to the implementation of more comfort variables to create comforts, and also by recognizing that we all have different individual cooling needs through an occupant-centric design. We need to realize that comfort is not only temperature, and using more comfort parameters, such as air speed or radiant temperature, we can modify the temperature range or comfort zone in which people feel comfortable. And this is quite interesting for cooling. In this figure, in these 2 figures, we compare 2 different set point temperatures. In this case, we are using, in both cases, a dry bulb temperature of 27 degrees Celsius, the red point, the red dot. And we have different comfort parameters. In this first figure, the air speed is close to 0. So we see as the comfort zone is totally outside the dry bulb temperature. So in this case, we are feeling heat stress. We are totally outside the comfort zone. However, if we increase with the same dry bulb temperature, we increase the air speed, we are able to start feeling comfortable. So this is quite interesting for cooling because we have a huge opportunity for reducing cooling demand and energy consumption only by using more comfort parameters. Because only by modifying the standard set point temperature by 1 degree Celsius higher, we can reduce energy consumption by close to 10%. So we should move beyond the classical approach that reduces comfort to 1 variable temperature, and we should start looking at an hybrid approach where we create comfort using more comfort parameters. For example, in these scenarios, we see as if we move the set point from 24 to 27, we can reduce energy consumption in order to 20%. Of course, that will depend on the final climate zone, but around the energy consumption will be reduced in the range from 10 to 30%. Additionally, we need to consider that all occupants will have different comfort requirements. It's important to start implementing adaptive environments. For example, introducing personal environmental control system. The target is to expand even more the comfort range in which people feel comfortable in order to be able to modify to reduce the centralized cooling needs that we need for the building. This strategy can help even more to downsize centralized cooling systems, reducing peak cooling demand of the building, decreasing investment costs, and reducing the energy consumption, mitigating the operating costs. The idea is basically cooling people and not the buildings by using more comfort parameters and implementing adaptive environments. The target is so to shift from a building-centric design to an occupant-centric design. If after these 6 steps, we still have cooling needs, finally, we have 2 steps more that will help mitigate the solar consumption and the environmental impact of cooling. They are related to the focus on the life cycle in order to select super efficient equipment in real operating conditions with high durability, adequate maintenance, and using ultra-low global warming potential refrigerants, and integrating more renewable energy in order to reduce the fossil fuel dependence. In this case, regarding the focus on life cycle, business models should move from a product-oriented system to a product-service system. For example, adding more features or services in the contracts, such as maintenance, repair, or replacement, in order to extend the product life cycle with longer durability and performance. In this aspect, in the next presentation, Dr. Giovanni Palafox will introduce more details about this. Moreover, the environmental consideration should be going beyond the standard operational phase of cooling technologies. And here it's extremely important to start considering the humidity influence in system performance. That is something completely overlooked since none of the system efficiency metrics of cooling system accounts for the humidity influence. And also the use of ultra-low global warming potential refrigerants. This should be a priority since F-gases can leak from units and quickly accelerate global warming, up to 4,000 times more than carbon dioxide in the short term. Finally, to mitigate carbon emissions, we need to create green energy demand in order to integrate more renewable energy. Here, thermal energy storage and energy flexibility can play an important role. And this is very important in cases of cooling. In the cases of cooling, since cooling flexibility can benefit from 2 important aspects. First, if we operate the system in better operating conditions, for example, at night, where we have lower temperatures, we can increase the seasonal efficiency of the system, even by more than 20%. If we combine this reduction of the seasonal efficiency with a lower electricity tariff, we can reduce the operating cost of the system by more than 50%. Following these steps, sustainable cooling can be guaranteed. And the most important thing that I would like to transmit in this presentation is that all these actions require time, require a long-term planning. We will face some heat events in the summer, and you will remember this presentation with these cool concepts. However, the easiest and fastest response will be to buy an air conditioner. So it's important to start addressing these actions in our home, in our houses, and of course, considering heating and cooling as a whole in the building design process. And this is the end of my presentation. Also, please remember that you can subscribe to our newsletter to keep updated with the last news on cooling. And you can also follow us in our social media profile. Thank you very much.
Brilliant. Thank you. Thank you very much.